All right, so we're going to look at similar polygons over the next 2 days. And so let's review some polygon vocabulary. What does it mean when two segments are congruent? What do you mean?
They're congruent.
Yeah, I was yawning.
What's equal? Their lengths. So, so they have the same length. What does it mean when two angles are congruent?
They have the same measure.
There you go, they have the same measure. So I want you to measure the following segments. Now, if you don't have a ruler, how could you measure the segments to see which ones are the same length? Couldn't you take a piece of paper and measure one of them and then apply that to the other ones? Yeah? So I want you to figure out which ones are equal. Because just because we don't have a ruler doesn't mean we can't figure out their length. So grab an extra sheet of paper from someplace and measure the first segment. You have to actually borrow paper from somebody. If you don't have your own paper. So I want you to discuss. I'm going to give you literally 30 seconds to discuss. Based upon doing that, which segments are the same length?
Yes, I'm using it to measure. You gave Brenna them. Don't worry about it. Olivia, I've known you since like kindergarten.
What? Did you say about kindergarten? Those were six.
What do we come up with out of the four, or I guess there's 5 segments?
4.
The first 4 are all the same length?
No.
No, they're different lengths, but
1 and 2.
2 of them.
No, 1 and 3 and then 2 and 4.
1 and 3 and 2 and 4?
If not,
I can tell you that 2 and 4 are not the same length, just visually.
No, it's these two. It's 1 and 3.
Yeah, 2 and 4 are the same.
Put on trace.
Oh,
2 and 4 are not the same length.
What?
1 and 3.
1 and 3 are the same length.
Yeah.
Oh, Olivia, you're so smart. Okay.
Yeah, Bailey, seriously.
So 1
That's what I added.
and 3, if you measure them, 1 and 3 will give you the same length. All right, so then let's look at our new vocabulary is similar. Does similar mean identical?
no.
Have you ever heard of similar twins?
I mean,
No.
Yeah.
Yeah, they're either identical or fraternal, right? So if things are similar, like for instance, you all belong to a family, whether you like your family or not. You all belong to a family. Unless, listen, unless you were adopted, and oddly enough, and research will show this to be true, even if you're adopted, you take on certain characteristics of your family.
what?
Like eyes?
Well, it's odd because even though genetically you may not have anything in common, you will start to take on certain traits or just maybe start just by facial features, just by how you express yourself, you just might, people will look at you and go, oh yeah, you look like your mom. You go, well, we're adopted. So, all right.
That's creepy.
Yeah, no, isn't that weird?
Isn't that like when
But
people start to look alike?
aside from people being adopted, you can tend to look at things in your face, and aren't they similar to maybe things in your mom's face or your dad's face or that kind of thing? Or you might act in a similar fashion to your mom or your dad or that kind of thing. So, however, my daughter, I call her my mini-me. My daughter looks very much like me, only she's the younger, prettier version. But people will say to us, "Are you sisters?" I go, "Oh, you're so sweet." No. But we're not identical, but we look similar. So similar things are not identical, although they could be. Could you say that two identical twins are similar? Sure, you could say they're similar because they share features, right? But look at the actual definition of similar. Things that are similar are alike but not identical. But not identical. So here's our point. If we're looking at, and you can see down here, these two quadrilaterals here, we could guess that they're possibly squares. And so if we're guessing that they're possibly squares, we're guessing because I don't see any right angles in there. I don't see any markers that tell me that all sides are equal. But I can guess that they resemble a square. Are they the same size? No, but they're the same shape. So they're not identical, but they're similar because they have the same shape. So our math usage here is going to be figures that have the same shape but not necessarily the same size are similar. There's going to be a little bit more involved than that, but we'll get to that in a minute. So how are the two squares, and now they're telling you they're squares, how are the two squares at the right similar?
They're both squares.
What makes them both squares?
They both have 90 degree angles.
Okay, they both have 4 right angles and all 4 sides are congruent. That's a congruent marker, not a triple equal sign.
Is that such thing?
No. How are the squares not similar?
The sides are bigger.
The length of the sides of the squares themselves are not the same, right? So these squares, sides to each other, I guess, are not the same. The same length. You could say the ratio of side lengths are not the same. I mean, that would be a more technical math way to say that.
Will the ratios be the same? Could it be like 1, 1, 1, 1, whatever those would be?
Okay, yeah, the ratios are going to be the same. Technically, we're going to get into that. But it's not 1-to-1.
Yeah.
Does that make sense? Okay, so then let's look at the next page. So here's a key concept. Two polygons are similar polygons if corresponding angles are congruent and if the lengths of corresponding sides are proportional. So here's an important part. I want you to highlight this entire statement here. An important part would be that two polygons are similar if and only if corresponding angles are congruent and if the lengths of corresponding sides are proportional. So corresponding angles mean angles that are in the same position. They have to be exactly identical. So they have to have the same angles, interior angles, but their the proportion of their corresponding sides or the ratio of their corresponding sides are proportional, meaning, and that's what Tatum and I were just discussing, if the ratio of the sides are 2-to-3, then all the sides have a ratio of 2-to-3. All the corresponding sides do. So let's look to see what that looks like. So look at the two quadrilaterals below. You're to draw a line from each angle in column A to its corresponding angle in column B. So here's A. What angle over here corresponds to A? Gee, don't they have them color coordinated for you? Oh, you can't see that on your paper, do you? So see the reds, and they're both marked with a right angle. Of course, that's a right angle too. But this is in the lower left, lower left. These are oriented correctly. If your polygons are not oriented correctly, you're going to want to redraw one of them so that they are oriented correctly, so that you can match up the sides and match up the angles. And so A should correspond to G. So A goes to G. What corresponds to B? H. And then what corresponds to C? And then what corresponds to D? And that leaves J, right? Then number 10, complete the extended proportion to show that all corresponding sides of the two quadrilaterals are proportional. So you really have not a proportion with 2 ratios, but you have a proportion with 4 ratios. And so we're going to look at all of those. So what they've done is they have AB, so here's AB over GH. Well, AB belongs to this quadrilateral, GH belongs to this one. This is a smaller and this is a larger. So they are putting small to large. You could have had large over small. It doesn't matter. This is not the only way to set up that proportion. And so the purpose of the last section was for you to realize that not everybody's going to set up their proportions the same. So they're choosing to do small to large. So you have to do small to large. So the next one that they've given you is BC. Well, BC is right here. What corresponds to BC on the big one? HI. So this is HI. High. And then this time they've kind of turned it around a little bit. They've given you the large one, which is IJ. IJ is over here. What does that correspond to the small one? CD. And then last, oops, no wonder. Last is AD. What does that correspond to? GJ. All right, so let's do problem 1. Let's see how this applies. And when you do your homework tonight, we're not going to get through all of this lesson today, so, well, the homework I've assigned should cover everything that I talk about today. So you have D, E, F, G, and then this symbol right here, that means similar to. So there's a new symbol for you. It's just a squiggle. It's a tilde, a squiggle. You like that word, tilde? So it says, what are the pairs of congruent angles? So those would be the corresponding angles. And what is the extended proportion for the ratios of the lengths of the corresponding sides? So you go ahead. How are you going to figure that out without a picture? You're going to draw a picture, and it doesn't matter what quadrilateral you draw. And you don't know which is smaller and which is bigger because they don't tell you, so it doesn't matter. So if I were you, I would start off by just drawing, I don't know, any similar looking quadrilaterals. How do I name a quadrilateral? And this is one reason why they don't give you a picture. If I put, let's just say I put D here. Oh, that's a D. Shocking but true. Let's try to make that look a little nicer. If I put a D there, all right, whatever. If I put a D there, can I put the next letter E? Can I put the E right here? Could I put the E here? Could I put it here? Yes. So I have to go either clockwise or counterclockwise. So don't forget you can't go across the polygon. So I'm going to name this D, E, F, and then G. And then I'm going to name this one, if this is D here, what should this one be? H. And I'm going to go in the same direction. H, I, J, K. So you just want to double check and make sure that what lines up here lines up here. So H, oh, did I see? I can't read my writing. This is why I'm double checking. Where's my eraser? Seriously. Oh, there it went. So I want to, oh, it won't let me erase anymore. Fantastic. All right. so H, J, we'll just fix it, K, L. How about that? This won't let me erase it anymore. All right, so again, double checking. So D should correspond to H, so D corresponds to H, right? E corresponds to J, E corresponds to the red J, we're looking at red. And F corresponds to K, F corresponds to K, and then G corresponds to L. G corresponds to L. So are we good? All right, so fill in the rest, if you haven't already. So correct me if I'm wrong. Are those your answers? So they kind of, waffle back and forth there. In our picture, we let the D, E, F, G be the smaller figure. So when you're doing your proportion, since this is smaller and that's larger, and they started off with DE over HJ, DE belongs to the small, and HJ belongs to the big. So I did small to large, just to remind myself, so that when you get over here, that you're doing small to large, and the only side left over is DJ, and that corresponds to HL. So are we good with that? Okay. All right, so then let's look at scale factor. So they've given you this word here, scale factor. We're going to use that a lot. So your scale factor is the ratio of the lengths of corresponding sides of similar triangles. So if, for instance, above here, the length from G to F was 2, and the length from L to K was, I don't know, let's let it be 14. Our scale factor could be one of two things. It could be 2 to 14 or 14 to 2. It depends on how they want you to write it. And doesn't that reduce to 1 to 7 or 7 to 1? So in our case, if GF was 2 and LK was 14, our scale factor would be 1 to 7. Would not my bigger polygon be 7 times as large as the smaller polygon in lengthwise? So really your scale factor is something that we use to multiply to dilate something larger, or divide to dilate something smaller. You can dilate things smaller. All right, so then let's look at problem 2. Are the polygons similar? If they are, write a similarity statement and give the scale factor. So you'll look at the proportion of their corresponding sides. That gives you the scale factor. You have to check every single corresponding pairs of angles to make sure that they're equal, and all 4 of the corresponding proportions to make sure that they're equal. It's not good enough to just have 2 or 3. They all have to be equal. And so question 13 says, circle the short sides of each rectangle. So for the small rectangle, what are the short sides? KL, right, the 10, KL, and the opposite one, MN, correct? For the large triangle, large rectangle, what are your short sides? So this one's 15 and this one's 20. So wouldn't XY be the short side? So, and they're asking you this on purpose because XY is the short side and the side opposite, WZ, is the other short side. Are the rectangles oriented correctly? Look here again. This left side here, isn't this the large side on this one? And isn't that the small side? Is this the large side here? No. These appear to be oriented correctly because they're rectangles, but they're really not. So in reality, if I were you, I would cross out one of these and redraw it. So I'm going to redraw the bigger one. I'm going to redraw it, squeeze it in here. Well, I guess I should redraw it so it looks proper, right? So I want to make it, try not to run into my answer there. So my short side should be here at 15 and here at 20. Oh, nope. My 20 should be here. So that means I'm going to turn this over here to the left, right? True? So if that happens, where does the X go? Where does this X go? I'm moving it over here to the left. Doesn't the X go where the W is? Okay, so then my X is here, and then my W gets moved down here. So my W is now here. And then my Z gets moved over here because I'm going counterclockwise. So my Z gets moved over here. And that leaves what left over? What's missing? The Y. So there's my new picture. I just rotated it a quarter of a turn to the left. And so now you can write the ratios of the corresponding sides. So they've started off here with KL over XY. Well, KL belongs to the small, and then here's XY. Are those corresponding now that we've redrawn it? Yes. And so they're going small to large. So if I were you, I would put out here small to large. That's actually an L. Small to large, to remind yourself that you're doing small up top and large on the bottom. So let's finish out their ratios. And so they already did the first one for us. Doesn't 10 over 15 reduce to what? Yep, so 5 goes into both of those. 2 and 3 times. Now I'm going to show you how if I were you I would be setting this up, but we'll do that in a minute. So LM corresponds to YZ, so that's 15 to what? If that's 15 here, then this is 20. What does that reduce to? 5 goes into both of those, so that's 3/4. Is that the same scale factor? Right there we could stop and say, are they similar? No, they are not similar. So just right here, scale factors are not equal. So figures are not similar. Yes?
Problem 1, like how can you say that D is congruent to H when there's similar figures and then you actually have to...
Are you talking about the one above?
Yeah. Like how can
Because they told you, they gave you that similarity statement.
they're similar? Because anytime congruent figures congruent.
No, because not all congruent figures, okay, all congruent figures are similar. Because the definition of similar figures would be all interior angles, all interior corresponding angles are congruent, and all corresponding sides are proportional. So if you have 2 congruent, equal size, equal shaped figures, that's going to match that definition. So technically identical shapes match the similarity definition. But not all similar figures are congruent. Because most similar figures are different sizes. Same shape, but different sizes. And so the one above said that they're similar. So they're telling you that it matches a similarity definition of all interior corresponding angles are congruent and all corresponding sides are proportional. So even though we don't see the picture, we know that. Whereas here, they're giving you the picture and we're making that determination. Are they similar? So we have to determine, first, are all the corresponding angles are congruent? Well, that was easy because it's a rectangle. So now we have to look at all the proportions of all the corresponding sides. So we are going to finish off these other two. So MN is here. What's that length? 10. And then they've already given you the other one. So 10 to 15 is what? So that's 2/3. And then NK is here, yep, 15. And then WX is 20. So we have 15 to 20. And that also reduces to 3/4. So let's just go back to the definition of similarity. Up here. What did the definition of similarity say? If the lengths of the corresponding sides are proportional. So the lengths of the corresponding sides are proportional, aren't they? But do they all have the same scale factor? No. And if you look at up here, remember this right here? See how they could set them all equal to each other? That implies that all 4 of those corresponding sides should be equal. We're not done. I've got 2 more minutes, so quit packing up. So notice how all 4 of those are equal. They're trying to trick you on this one. We've got 2 sets here, that 2/3 and that 2/3. You could go, okay, those are the same scale factor, and those are the same scale factor. So that means that the figures must be similar. No, because all 4 need to be the same. And so all 4 of them are not equal. You ought to be able to set all 4 of these equal to each other and they should be the same thing, which they're not. So don't fall into that trap. All right, we will finish up the rest tomorrow. It's possible that you might get stuck on one of your questions tonight, but I don't think so. I think we'll be okay. All right, so look at question 15. We're going to place a check in the box if the statement is correct and place an X if it is incorrect. So they say that polygon KLMN, what's that squiggle mark mean? Similar to polygon XYZW, and the scale factor is 2/3. True or false? Are they similar? Did they meet the definition of being similar? No. So they are not similar. So we're going to put, be helpful if I had my pen checked. So we're going to put an X there because that's wrong. And the second statement again says that they're similar. I don't even have to read what the scale factor is. Isn't that also incorrect? Because the figures are not similar. And then the last statement says the polygons are not similar. That one's true. So we're going to check that one. Then let's look at problem 3. Bless you. They tell you in the directions here that polygon ABCD is similar to polygon EFGD. So what they're actually telling you is that all corresponding angles are congruent and all corresponding sides are proportional. The minute they give you that similarity statement, you can assume that. And it goes on to say what is the value of Y. So I'm going to kind of ignore what they had over there. So we're not going to really follow these. We might as we do it, but let's do our own work over here off down here. So as I look at the picture, don't I have overlapping polygons? Here's my smaller one and here's my bigger one. When they overlap like this, they are oriented correctly. If you don't like the fact that they're overlapped, you can redraw this one down here if you like. But wouldn't you agree that both polygons share angle D? And so obviously, whenever you have overlapping polygons, if they share an angle, you can assume, even if you don't know what the angle measure is, that those angles are congruent. I don't know what these two angles are, but again, because they gave me the similarity statement, I know that they're congruent and so on. Let's set up our ratio of proportional sides. I know this little side from D to E is 6, and I know this side from D to A is 9. You always want to choose two sets of corresponding sides that you have both measurements to, because when you set up your proportion, you need one ratio that you have both numbers for. So I'm going to choose to set up my proportion with DE is proportional to DA equals, and I'm going to stop here for just a minute. DE belongs to the smaller figure and DA belongs to the larger figure. So I want to make sure that I write over here that I'm going from small to large, because my other ratio on the other side of my proportion has to be from small to large. So if I'm trying to find, and we can choose, you want to find Y first or X first? Doesn't matter. All right, so we'll go alphabetically. So F to G is where our X is, and that belongs to the small figure. So don't I want to put it up here in the numerator? So I'm going to put FG here, and then what corresponds to FG on the big figure? BC. So then fill in your proportion with the corresponding values. So DE is 6 and DA is 9. FG we don't know is X, and BC is 7.5. Now you could choose to reduce this fraction here before you multiply. I probably would, especially if I'm not using a calculator. So doesn't 3 go into both of those? So 3 goes in here twice, and 3 goes in here 3 times. And then we're going to use cross products. So 3 times x is 3x equals, and what's 2 times 7.5? 15. And so what does x equal? 5. So there's one of our answers. So x equals 5. And then let's set up another proportion. So we want to find y. So we're still going to use DE and DA equals. Y belongs to our smaller figure, so that's EF. What corresponds to EF on the big figure? AB. So we want to fill in the corresponding values. So again, DE is 6, DA is 9, EF is Y, and AB is 5. I would again reduce this. 3 goes in here twice, 3 goes in here 3 times, and cross multiply. 3 times y is 3y, and 2 times 5 is 10. So what is the value of y? I would prefer that you wrote it as 10/3 rather than a decimal. If you write this as a decimal, what's wrong with that? Isn't it 3.33333333? Doesn't the 3 repeat? And most of you will write it as 3.3 or 3.33. Is that answer as accurate as mine? Yes or no? Mm-mm. So, especially if you have a repeating decimal, don't turn it into a decimal. So here's our other answer. If you're taking that Common Core test, you need to answer the question a complete statement. So therefore, oh, they only want to know what the value of y was? Well, that's odd. We found the value of both of them. So therefore, the value of x is 5, and the value of y is 10/3. Who are you looking for? Oh, yeah, Asa. All right, so then let's do problem 4. This one says a rectangular poster's design is 6 inches high by 10 inches wide. It's not a very big poster, right? What are the dimensions of the largest complete poster that will fit in a space 3 feet high by 4 feet wide? So determine how many times the design can be enlarged. In other words, what are they looking for? What are they actually asking for? How many times can the photo be enlarged? What is that in reference to similar figures? Nobody has an idea? How about scale factor? Isn't scale factor the number of times one of the figures is larger versus smaller than the other one? That's what that scale factor means. So watch what they're asking you to do. Determine how many times the design can be enlarged. So the height, 3 feet, is to how many inches? Which one? Does it matter what we put in there, 6 inches versus 10 inches? Because did they give you the height? Did they tell you which one was the height? Up here? Did they tell you which one was the height? Yes, they did. And what if they hadn't? How would you know which one went with 3 feet? What if they hadn't said that 6 inches is the height and 10 inches is the width? How would you know?
Because it says 3 feet is the length.
Well, 3 feet versus 4 feet, isn't 3 feet the smaller number in the 3 feet and the 4 feet grouping? And so you would choose a smaller number over here to go with that. So if they hadn't told you, you need to correlate the smallest figure with the smallest figure and the largest with the largest. So for this one, we're going to have 6 inches. Actually, wow. I don't know if that's what they want. I think they want to know what actually is 3 feet. So how many inches is 3 feet? 36 inches. And how many inches is 4 feet? 48 inches. So we've got what inches divided by 6? What are you doing? What are you putting in here? Yep, the 36. And divided by 6 inches does indeed give us that 6. What does the 6 represent? Looks like that, right? And then you're going to take your 48 inches here. That actually is an 8. Shocking but true. And divide it by 10 inches. Where'd they get the 10 inches? So the 10 inches came from here, because that's width, and the 6 inches came from here, because that's height. And so all they've done is they've taken the 3 feet over here. So we had 3 feet is to 6 inches, as 4 feet is to 10 inches. So that would have been our original proportion. Can we compare feet to inches? Yes or no? Nope. So that's why they went ahead and made these conversions here, because I've got to substitute in either feet for inches or inches for feet. It's much easier to take the larger measurement and convert it to the smaller. So instead, we now look at the following proportion. And we have substitute in for 3 feet the 36 inches, and then for 4 feet the 48 inches. And then look at, do they give you true proportion? Is that a true proportion? Let's look at their cross products. What's 36 times 10? 360 inches. Does that equal, what's 6 times 48? What's 6 times 8? What is 6 times 8? What did you just say, Tatum? Thank you.
Wait, 6 times 8?
6 times 8 is 48, right?
Yeah.
Okay.
That's
So,
what I meant.
I couldn't hear you over what they were saying.
Oh.
And then 6 times 4 is 24, plus the 4 is 28. I thought you were giving me the whole value.
Oh.
And so, are those equal? No, they're not equal. So this is interesting. Have they given you similar figures? Have they given you similar figures? No. So really the rectangular poster is not a similar figure to the space in which it's fitted into. So my point is, if they were to enlarge it, it's not going to enlarge and fit perfectly in that space because they are not similar figures. So when we look at these values here, the 6, so when you look at the 6 and the 4.8, do you notice that those scale factors are not equal? Right? So the question says the design can be enlarged at most how many times? Which is the smaller of the two? The 4.8. Because if we try to enlarge it by 6, what happens if I multiply this dimension by 6? What does this become? 36 inches. And that'll fit here, right? But what if I multiply this by 6? I get 60 inches, right? And will that fit in this? No. So at most, we can only enlarge it, 4.8 times. So they are not similar figures. So we have to choose, because it's a restricted space, we have to choose that smaller scale factor. And so write in here that they are not similar figures. If they were, the scale factor of all corresponding sides would be the same. So then the question 19 says, let x represent the height of the poster. Write a proportion and solve for x. So we know we already have 6 inches by 10 inches. So we're going to go, let's go width by height. And we're going to go 6 inches is to 10 inches. As, if I'm going to let x represent the height, where does it go in the, on the right side? Does it go in the numerator or the denominator? The denominator. And so what am I going to let the width be then? Go back to this. If I'm going to use this as my scale factor, I could multiply 10 by 4.8 and I would get my 48 for my width, right? And that would fit in there perfectly. And if I multiply 6 by 4.8, shouldn't I get less than 36? So which is the height which is the one that we know? We know the width is going to be 48 because that's the one that matches that scale factor. So we're going to put that 48 in here because that's the one that it's fitting perfectly into. And so then we're just going to cross multiply. So from here we have 6 times x is 6x equals, what's 10 times 48? 480. Divide by your 6. I'm having issues with making 6s today. How many times does 6 go into 48? 8 times, and 6 goes into 0? 0 times. So isn't that 80 inches? So the largest complete poster that will fit would be 48 inches by 80 inches. Does that make sense? Something's wrong.
Don't you already know the height for x? Because you found 48, so now you know that 36.
No, we don't know the height because that's why we're letting x represent the height of the expanded poster. right?
Just 3 feet.
But the height of my original poster is, oh, I have that backwards. No, I don't. Yes, I do. That's why. Bummer. What do I have wrong here? Yeah. Yeah. Let's see if it'll let me erase any of that. Oh, I don't want to erase all of that. Hang on. Oh, isn't that an awesome feature? No, stop it. Oh. Okay, well, let's not worry about that. Oh wait, look, it came back. Oh, good heavens. But now it won't let me erase it. Okay. Well, yippity skippity. Technology is stressing me out. All right, so this should have been 10 inches, right? This should have been 10 inches. And this, the 10 inches should have been my 6 inches. Yes. Oh, please. Somebody take her. Will you go take her?
Okay. Stand.
Oh, hang on.
Okay.
All right. So back to what we're doing here. Shh. So my mistake. It'd be helpful if we paid attention to the fact that the 10 inches is your width and the 6 inches is your height. How did I know that something was wrong though? What was my answer here? It was 80 inches, and it cannot be bigger than the 36 or the 48, right? So something was wrong. So now let's go ahead and what does go here? What's the biggest width we could have? The 48. So we're going to put that 48 here. Now let's cross multiply and solve. So the 10 times the x is 10x equals 6 times 8 is 48. 6 times 4 is 24. Plus the 4 is 28. And so now when we divide by 10, what are you going to get? 28.8. Does that seem more reasonable? Yeah, because the 28.8 is less than the 36 and it's less than the 48. And really the height that we're looking for it to be less than is what? Isn't this the height that we're looking for it to be less than? So, therefore, the largest complete poster that will fit is, our width is 48 inches by a height of 28.8 inches. You okay with that, Tatum?
No, I'm confused.
About?
Not what you got,
Right.
but like, I don't know.
Well, now these dimensions are similar, make this a similar figure now. The 6 inches
No,
by
I get
10
what you
inches.
did, I'm just confused with the question.
Because since these are not similar figures, in other words, since the poster and the area at which the poster goes in are not similar figures, they're both rectangles, but their corresponding sides are not proportional. So if we were to expand this poster here into that space, it is not going to perfectly expand into a 36 by 48 inch poster. And so rather than, since we can't go over the space limits, we had to go under the space limits. Does that make sense? Okay, and so we're using our knowledge of similar figures to do so. All right, so let's look at problem 5, which would be on so look at the scale drawing. What bridge does that appear to be? Appears to be the Golden Gate Bridge. Use the scale drawing of the bridge. What is the actual height of the towers above the roadway? Use it. Oh, well, we're not going to use a centimeter ruler. Mostly because I can't do it on here. So I guess somebody have a centimeter ruler. You want to measure on your paper what that distance is. So use a centimeter ruler to measure the height of the towers above the roadway in the scale drawing. So you only want to measure from here to here. So you don't want to measure this part that's down here. That's what I'm reading it to say anyway.
It's like half a centimeter.
Is it half a centimeter? So we'll do 0.5. Label the drawing with a height, so that's what we did. Identify the variable. Let h equal the blank of the towers. So what is it that we're trying to find?
Don't you just want from like the roadway up?
Yes.
That's half a centimeter. Yes, it is. I'm sure I'm not using inches.
You call
Here.
All right, let me get out my ruler since there appears to be a disagreement.
It's half a centimeter. It's half a centimeter.
Let me see your paper. There appears to be a disagreement. Okay, so it's a little smidgy over. It's 5, 6, 7. 7/10. Are we going to agree with 7/10? What'd you have, Eric? Oh, okay. Then let's use 5/10 because it's easier to work with. Although, having said that, if it's 7/10 and we choose 5/10, are we going to be as accurate? Let's go ahead and use 7/10 just for accuracy purposes. All right, so identify the variable. Let h equal the blank of the towers. What is it that h is going to represent? What are we trying to find? What's the question? Right, so this is our question. What is the actual height of the towers? So we're going to let h be the actual height of the towers. So use the information on the scale drawing to write a proportion, then solve to find the value of the variable. So hint, 1/200 is equal to the tower height in the drawing to the actual height in meters. Where did they get the 1/200? Right, look at the scale. Look at the scale here. Is the scale in equal measurements? Centimeters and meters are not equal measurements. So remember we talked about the other day, King Henry died while, that would be grams, meters, liters, drinking chocolate milk. So if I were to put 1 centimeter here and I wanted to convert it to meters, isn't meters right here? So I want to move this 1 centimeter, I want to move this that direction, don't I? Yes or no? So how many places do I move it? 2 places. So my decimal point would be right here. So if I move it 2 places, it would be 1 centimeter would equal 0.01 meters, and vice versa. What would 1 meter equal? If you went backwards, if we put 1 meter here, we have 1 meter here, what would it equal in centimeters? You're moving it 2 places to the right, so what would it equal? 100. So 1 meter would equal 100 centimeters. But the scale drawing says, bless you, the scale drawing says that 1 centimeter equals 200 meters. So I guess our scale actually doesn't matter here. This is really our 1 centimeter. For every 1 centimeter, we have 200 meters. So if they had given you 2 inches equals, let's think of a map. If they gave you 2 inches, and that is equivalent to 100 miles, wouldn't you be putting in here 2 over 100? Yes or no? Because you'll see that scale on your map. All right, so which do we not know, the tower height in the drawing or the actual height? The actual height. So set up your proportion. 1/200. I would assume they're going to have to use a calculator for this. They're big numbers. We know our tower height in the drawing is 0.7 over, and we're going to use h. So cross multiply to solve. 1 times h is h. What is 200 times 0.7? We can do that without a calculator. What's 7 times 0? 0. 7 times 0? 0. 7 times 2? 14, and then you've got to put in 1 decimal place. So isn't h equal to 140 what? If this is centimeters, what was this one down here? Meters. So then my answer here is meters. So the actual height of the tower above the roadway is 140 meters. And then the last thing I want you to do is answer questions 25 through 27. And determine what the 3 similarity statements would be. And 27 is just getting you to identify the corresponding angles, and you could write 3 different similarity statements for those 2 triangles, depending upon what order you put the angles in. So while you're working there, I'll put the answers up here. You can't see them. Bless you. Bless you. Bless you. Not today. Alright, so those are the answers that you should have gotten. Any issues? Okay. Alright, so then let's look at your workbook. So go to page 187 in your workbook. And I want you to look at question number question number 7. Question number 7 says an equilateral triangle. So we have an equilateral triangle with side lengths 6. In an equilateral triangle with side length 15. The question is asking, are the polygons similar?
Yeah.
What are your thoughts? Why do you automatically say yes? All their interior angles are the same. What are the interior angle measures of all equilateral triangles? 60, 60, 60. It doesn't matter what equilateral triangle it is, right? So what's the other piece that's missing? Are all the corresponding sides proportional? What's the scale factor for all corresponding sides? 6 to 15 or 15 to 6, right? And then you would reduce that scale factor. Are all 3 corresponding sides that same factor? Yes. Would that be the same? Could I say that all isosceles triangles are similar? Could I have an isosceles triangle, could I have 2 different isosceles triangles with proportional legs, but the bases aren't proportional because the vertex angles are different sizes? I could, right? So any figure that has all 4 sides equal and all interior angles, as long as your interior angles correspond to the other figure's interior angles, and let's think about this. Let's just think about a 4-sided figure. A 4-sided figure with 4 equal sides could either be a rhombus or a square, couldn't it? And what do all the interior angles have to add up to? On a 4-sided figure, 360. In a square, two different squares, two different side lengths. Are all the interior angles equal? Yes. What about a rhombus? Are all interior angles equal in a rhombus? No. But what do you know about the opposite angles in a rhombus? They're congruent. So long as the two rhombi, the two different sized rhombi, so long as their interior corresponding angles are the same measure, then if they're then their sides will be proportional. So that's the only thing that's different here, because a rhombus is not equiangular, where the square is equiangular, the equilateral triangle is equiangular. So if you start to look at something like a rhombus, then you have to consider those angles. So just be careful with some of those. All right, so the answer to this one is yes. Then I want you to turn the page, and let's look at number 11. So it says an architect is making a scale drawing of a building. She uses the scale 1 inch is equal to 15 feet. Isn't that just like the bridge one that we were doing? And part A says if the building is equal to 48 feet tall, how tall should the scale drawing be? So x is equal to height of scale drawing. So I want you to figure that out. Write a proportion. You already know this is one of your ratios. Even though it's inches and feet, we don't have to care on the scale drawing. So this is one side of your proportion. So you're either going to have 1 over 15 or 15 over 1. And then on the other side, you need to set them up in the correct order, because as you found out with our one problem, if you put them in the wrong order, you're going to get the wrong answer. So I want you to compare your answer with those around you. What'd you get? The what? What'd you get? I heard that. 3 what? Did everybody get that? 3.2 what? Chicken toes? Fuzzy navels?
3.2 Einstein mustache.
3.2 Einstein mustaches? I like that. So you need to have a therefore answer. So your proportion should have been either 1 over 15 equals x over 48, or 15 over 1 equals 48 over x. Either way, or there's actually 2 other ways you could have set it up too. Either way, your cross product should have been 15x and 48. So if that was your cross product, you know you set up your proportion correctly if it's different than mine. And then because it's a scale drawing, you could have had your answer for x in a fraction, a mixed number fraction, or in a decimal. Just be careful if that decimal is repeating, that you just keep it as a fraction instead. All right, so then do part B. and we'll be done. So part B, this time they say if the building is 90 feet wide, bless you, how wide should the scale drawing be? All right, so you go ahead and figure that one out. What'd you get? That one was easier, right? So we got 6 inches for that one. All right, we good?